very painful to really follow the trajectory of atoms that are subject to not only potential energy, but also kinetic energy due to the thermal vibration. So this is the framework. And I'm going to apply this methodology to a problem which is simple enough so I can show you the capabilities and virtues of this methodology. So let me start by talking a bit about hydrogen. Hydrogen in metal materials. So hydrogen can be stored in many different metallic materials, and in all the cases, what happens is that once you have can you see my mouse when it moves? Sorry.
Yes.
Oh, okay, yeah.
No?
Thank you.
I can see the point.
You see the point?
Okay.
Yeah. Okay.
Yes.
Thank you. So so the chemical equation that you are going to have is the metal material, the host material, and then you have hydrogen. So this hydrogen can be host in different metals. So what happens in all the cases is that you have a chemical problem, but you cannot avoid the mechanical problem, because when hydrogen diffuses inside of the metal, there is a deformation within the lattice, within the material. So depends on how fast hydrogen can diffuse inside of the metal, and the kind of deformation that the metal is going to suffer. So that metal hydride is better, is a good candidate or a bad candidate for the application that you have in mind. So those are the effects that you need to include in your model in order to decide which metal is better than others. So let me move. So you see this diagram. So the options are high. I mean, for different metals. Oh, let me see if I can move now. Yes. So as I said, for instance, in this case for magnesium, so you see how in this case is a nanowire. So how the nanowire is going to suffer very high deformations after only 10 cycles. So when you could like to store hydrogen in a material, you would like to do it several times and not only one time. So you need to really account for the deformation that you're going to have, that is going to accompany the chemical mechanism that you're going to have. So this is really what you need to be able to understand and be predictive about how good this, as I said before, this material is in comparison with other ones. So this is not only a problem that happens when you would like to store hydrogen in a material. This is a problem that you see or you had to face for different batteries, in this case, silicon and lithium batteries, problems that you need to address and need to understand well when you have high entropy metals, high entropy alloys that are now very interesting in many industries. So what happens when you have grain boundaries, and then one of the species are going to segregate along the grain boundaries, and so the material is going to change their properties. So is this good? Is this bad? What can you do to prevent that kind of damage or mechanical damage that you can have in the long time? It's not just something that you would like to study for a short period of time. You would like to be able to follow this problem through the life of the material. So Another role that are going to play are the nanoparticles within these problems, the size of the material, sorry. So are you going to observe the same properties when you are talking about the bulk material, or you are talking about nanoparticles? Do the nanoparticles behave better or worse than having larger sizes of your material? So it has been observed experimentally that nanoparticles can perform better than bulk materials, larger sizes of the material, because they are able, nanoparticles, to release the deformation much better during the loading and uploading and downloading of a material, in this case hydrogen, inside of the host material. So this is something that is interesting to know and to study and to evaluate. This is these are the results, experimental results of a group in Stanford, where you can see nanoparticles of palladium and how hydrogen goes inside of the material. And then you observe here these phases, different phases, alpha and beta, of the material of palladium with and without hydrogen. So you see how here in these figures, you see how the material with the two different phases, hydrogen gets inside of the material and the phase boundary propagates. So these kind of results are not very easy to find in the literature, and in order to inform always your model, you need properties of the material, and you need properties that in many cases, or all the cases, needed to be provided through experimental results. So in that sense, I mean, when you work at the small scale, it's difficult to find experimental results that really provide the properties. But in this case, I mean, when we study palladium, and this is why I'm going to present this application, hydrogen in palladium. So we found that these results that were very useful. You will see it during through my presentation. So as I said before, the length scale is nanometers because these are nanoparticles, and the tiny scale that you would like to be able to address goes from seconds to hours. So hours is not the tiny scale that is crucial for thermal vibrations. So that is why, in order to study the process through a larger time windows, so you need to be able to avoid the thermal vibrations. And this is what we think that we have been able to do with this methodology that I'm going to talk about. So yes, just to show you what I've been talking about, the vibration of the atoms, and you can see that in this movie, so the atoms are going to be moving all the time. And in some cases, you don't need to follow the position of all the atoms by themselves, but just the average trajectory. So what you have here are, I mean, the difficulties that you have is the existence of multiple scales. And the scales that you're going to have, as I said, the thermal by activation that you're going to have, then you have grain boundaries, you have defects at the atomistic scale. The majority of them are at these locations. And then you have the macroscopic processes that you would like to be able to study. So those are long-term transport phenomena. And so the difficulties are how to connect both, I mean, the scales for the atomistic scales, I mean, in terms of time and space, and the scales that are interesting for the daily for our life on the daily basis. So so you need to cross grain both scales for the in a space, so you can use techniques that allow you to include atomistic information and then be able to study larger domains. And for the time scale, you can use techniques such as molecular dynamics, but you would like to address time scales of higher values, I mean hours, minutes, and seconds, up to years. So if you use molecular dynamics as the methodology to solve to study your problems, so this is not easy to reach time scales of the order of seconds and hours. What I was, oops, do you see the movie? No? Rina, do you see the movie?
No, it does not move.
Oops, okay. Well, I'm sorry. So here in this slide, what I wanted to show you is how in this on the left, the atoms are going to be vibrating all the time, whereas here on the right, you don't see any movement of the atoms. So this is really what we would like to get. I mean, with this model, diffusive molecular dynamics, we would like to know the position of the atoms in average and not to follow the thermal vibrations. So let's see if you can see the rest of my movies. So the objective, the aim of the work is clear. I have said that before, to avoid thermal vibrations. And how do we do it? So we have been adding pieces and on top of another pieces in our methodology. So you see the first publication was in 2008, then more recent publications in 2015. So we have been adding, as I said, pieces so that our methodology can address more and more details. So this is in this picture, what you can see is what I was I've been saying since the beginning. So the trajectory of the atoms is the black line, whereas this is the red line is what is important for the problem that we have in mind. I mean, you don't need to follow this trajectory. Following the red one or accounting for the red one is good enough. What happened is that at the atomistic scale, you have interactions in between every atom and the neighborhood that the atom has. And you need to account for interactions in between those atomic atoms and anatomic positions. So you had to do that for describing the position of the atoms. And also you have to do that in order to study the chemistry. Let's say the chemical reaction that you're going to have. Is one atom going to move to another position or not? So it will depend on the environment that every atom has inside of, I mean, in the particular crystal structure that this metal have. That's why I was saying that I don't know how to extend this methodology to materials that are not that don't have a crystal structure. So let me move forward. So I try to avoid as much as possible the details of the formulation. I would like to show you more the capabilities of this formulation, this methodology. But just let me tell you a few ingredients of the formulation. So in addition to the we are going to have atoms, and we are going to have different species. So atoms, because we are going to need to know the position of atoms, and a position of the atom depending on the kind of material you have. If you have, as I mentioned before, you have your problem, you are interested on studying high entropy alloys. So in that case, a position can be occupied by magnesium or aluminum, if we are talking about that alloy, or if you have more species by many other species. So you need to include in your model positions and species. And also, in order to use non-equilibrium statistical mechanics theory or elements of that theory to include it in your methodology, so you need to take into account not only the position of the atoms, also the momentum. So you need more than the more variables, let's say, in your model. You need to know the positions, as I said, the momentum. Remember that the energy in this at the atomistic scale has always two components: the potential energy and the kinetic energy. Kinetic energy connected with temperature, and the potential energy let's say associated to the position and the formations and stresses and tension and everything. So yeah, so in order to take into account which atomic position is occupied by what species, you need to include the occupancy. So this variable, the occupancy, is going to tell you if one position is a position is occupied or not by a given species. When you have hydrogen, so hydrogen is going to occupy not the basic, the atomic position of the host material. Hydrogen is going to occupy interstitial positions. So the picture that is different when you have alloys that can substitute position of the matrix, or you have another species like in the hydrogen case, in which is going to these atoms of hydrogen are going to diffuse from interstitial positions to another interstitial position. So yeah, so how do we average this? Remember the picture I was showing before, the black trajectory and the red trajectory. So how are we going to average our fields that are part of our formulation? So using this expression, so based on non-equilibrium statistical mechanics. So I'm not going to get into details. I don't want you to get lost in the details of the equations. You can, of course, ask me or find it in the literature. Few words about the potential energy and the kinetic energy. So the potential energy is in our case, also in our formulation, diffusive molecular dynamics, and also in the molecular dynamics models or formulation, is taken into account through interatomic potentials. Here you see acronym for corresponding to different interatomic potentials that take into account more or less interactions within the material. But the important thing is that what the interatomic potential is telling you is the energy of the system written in terms of interactions in between atoms. At the atomistic scale, the material is discrete and is not continuum. So this is a main change in the framework when you move from atomistic to continuum models or macroscopic models to think in terms of discrete position of the every point in the material in this like in the continuum case. So you need to only you need to think on the material as a description, not on points everywhere, points, positions that are part of the crystal structure of the material. So yeah, so our with the principles of maximum entropy that we use, principles that are part of this formulation on equilibrium statistical mechanics. So we average both fields, the position and the momentum, and so the energy and the occupancy of the positions. So with that, and going very fast on this formulation because yeah, I don't want, as I said, I don't want you to get lost. So we can write this Lagrangian representing what is happening that has this term that accounts for the potential energy, and we have this other term. Mechanics is here, and this is the chemical part of the problem that you need to consider. So when you don't have diffusion, so this part is not included, and then you only have the mechanical part.
Pilar.
Yes. Yes.
I don't know if we have the same window as you do, but it seems that your mouse is moving, but moving in a blank area. So,
oh, really?
Yes.
What about now?
What do you have in your slide right now?
I have the Lagrangian, and then I have the grand canonical.
No, we only have the first line of your slide. Assume H is equal to the sum of HI.
Okay, yeah, no, I'm going through steps forward. So what can we do? What can I do?
I don't know what happened. Why your presenting is not on the screen.
Yeah, I haven't changed anything. Okay, let me move to the next slide and see what you can see. What do you see now?
We see the grand canonic free entropy.
Yes.
But only the
if
first.
I go back?
Yeah, but we see only the first line of the slide.
I don't know why. Okay, what can I do? Teams is not my...
Do you have a PDF? Maybe it's going to, I don't know why.
I have movies, so the PDF is not an option in my case. I mean, when I'm already talking.
Because we do not see any equations, because I see that you're moving, you're talking about the equations, but we do not see any equations.
Yes. Can I use another way of presenting the work or what?
Any way that we can see.
Okay, let me stop sharing and then I start again or what?
Yeah, you can stop sharing and sharing again. Let's see where we get lost.
Okay. Stop sharing. Okay, sure.
We still see your screen.
Yes, yes. Stop sharing. Yes. Stop presenting. Yes. Okay.
Now you.
Let me open then my. Okay. Share. What about now?
Now we see your first slide, the second one.
Yeah, I'm trying to move.
Okay. So far, so good. Now I stop seeing your equations.
So it's again the same. So what about if I do this? Do you see anything? No.
No, I mean, we only see the first line. Assume H is equal to the sum. That's the only thing we see.
I don't know if something that is only for this slide, or should we
Can you
continue
move forward?
Yes.
We see only this first slide again.
What about now?
Sorry, the first, the same.
My goodness. Okay. The same?
The same. So, I mean, so we see the first line, this one now, the closure, need evolution equations for beta and gamma, and that's it.
Meaning that you don't see any of my equations. What about this one?
This one, no equations.
Oh my God. And no figures, nothing.
Wow, there's a figure. Base letter side always occupied by metal atom. And then you have the XH fraction.
And you see the atoms or not?
Nothing.
So
why don't you, I mean, maybe the easy lesson is you try to print it to PDF. We can try to see your, at least the equations through the PDF. And when you need to show a movie, you share the movie.
Okay, sorry.
No, I don't know. It's either the problem of PowerPoint or Teams. So in any case, the fault of Bill Gates.
Oh. Now stop sharing and share the other one, or what?
Yeah, yes. Stop sharing and then share your PDF. Another thing, maybe you can share all your screen to
the full screen.
I mean, your desktop instead of just one.
Yeah.
One window. Sometimes it solves the problem.
It helps. Okay. Okay. Share. How do I share the screen? Okay. Okay. Window. Okay. What about now? Do you see my PowerPoint?
Yes. Can you move forward to see the equations? So if we can see something. Go ahead. Yes, now we see the equations.
Okay. Okay, I'm very sorry. I go fast on the equations, faster than what I was pretending to go, so you can see the results at least. Okay, let me summarize. So I was
Okay.
saying that, yeah, thank you, Rina. So I was
Welcome.
saying that you need to account for the potential and the kinetic energy. The way to account for the potential energy is through interatomic potentials. And since you have a couple problem, you have mechanics and you have the chemical part. So in this equation here, this Lagrangian, you have both parts, the mechanical part and the chemical part. Okay, so I yes, I go fast. So as always, you need to minimize the energy, and then you have you get your equilibrium relations. So you need you in this case you are going to have these are going to be your local equilibrium relations. I mean. In addition to the mechanical part, also the chemical part. Let me move forward. And yeah, so here again, this is, through the formulation, you are going to end up having this kind of equations. This is the entropy function, again, having the chemical part and also the potential part. And yeah, this is the equations for the mean field formulation. So here you have, this is the chemical part, okay. Here is the derivative for the, in terms of the position of the atoms. These are the equations that you end up solving the system of equations for the problem that you have. So, yeah, let me move forward. So the energy is going to have this expression. The energy, what is important here is that within our formulation, we can have the energy for each atom. And you see here this dot. So this is the evolution of the energy for every atom. And in this equation, so this is energy, and the other equation is mass, the chemical part. So we are able to have an equation for the evolution of the occupancy of every atomic position. So meaning that this is not so easy. I mean, to have a model in which you have the energy for each atom, so the total energy of the system is going to be the sum over all the atoms that you have in your model. So yeah, let me move forward. I don't have time now to explain these equations. So yeah, this is more important in order for you to get a picture of how we proceed in our simulation. So we start with a configuration of the of our atomic positions with empty positions for the interstitials in the case of hydrogen. So the dark dots are the palladium in this case, or the metal, and the blue ones are the atoms. So we start with a situation in which this is the surface, free surface. And remember that we are, I said that we were going to simulate nanoparticles, so we have free surfaces. So this is the surface, and hydrogen is outside in the air. So hydrogen is going to get inside of the material and occupy different layers of or positions. So the way we evolve is from this first initial configuration. We are going to move the atoms, and we are going, you see here, the atoms, sorry, the first step here is to diffuse atoms. So you see X is n in a situation n plus 1 in time. And in the next step, we are going to relax the position of the atoms. We say relax because once the atoms of hydrogen, in this case, get inside of the material, I mean, the atoms need to find another steady state situation of a local minimum of the energy, and then the atoms are going to move in order to release the value of the energy. So we continue taking steps in a chemical step and a mechanical step, so so that the diffusion takes place, diffusion of hydrogen inside of the material. So you see how the configuration is going to be evolving. So, and the question I have here, is this molecular dynamic or this is another diachronism for another model based on molecular dynamics, and the truth is that we are solving the position of the atoms and the chemical part too, but we don't solve the Newton's second law, which is what you solve in molecular dynamics, meaning that we don't follow the position of the atoms at every single movement. We average the movement of the atoms. Okay, so these are the first comparisons that we took for palladium. So you see here that here in the alpha phase there is no hydrogen, and in the beta phase there is hydrogen. So this is the phase boundary that is going to propagate through the material when the hydrogen gets inside of palladium. So why palladium and not another material? Well, because it's a very simple model. It's simple in the sense that the crystal structure of palladium remains the same. You only have the lattice parameter is the one that is going to change. So you have a change in volume when hydrogen gets inside of the material, but the crystal structure remains the same. For those of you who are not familiar with these formulations, the atomistic one is kind of avoiding a lot of problems because it's just swelling. The material is just swelling. We compare our results with previous results in the literature, and we found out that the lattice expansion that we observed were in good agreement with what has been observed previously. So you see here how when time evolves, so the hydrogen propagates inside of the material until the occupancy is 1, starting from occupancy 0. So here is what we are doing now. We are now finishing applications of the same methodology, but to a more complex metal, which is magnesium. What other features you have to have in mind and being able to model? Well, you need to decide at the very beginning what initial configuration you are going to have, whether you need to define more or less layers of the material occupied by hydrogen. So you need to see, what kind of properties, you're going to include in your model. So in order, you see in these figures that if you change the chemical potential, the amount of hydrogen that is the energy the energy of that you need to apply in order to introduce hydrogen, in other words. So you will see that depending on the value of this chemical potential, so you are going to end up having phase boundaries with a different shape. So this is the one that where this kind of phase boundary, very sharp, is the one that was observed in the experimental work. So this is the one that we really need to include in our model, meaning that this is the value of the chemical potential that you need to use for palladium and nanoparticles. So another study that we did was to compare different geometries. I said at the beginning that storing hydrogen in nanoparticles was observed to be more convenient because the small sizes of the material were able to release the deformations in the lattice. So is the shape of the nanoparticles also played into any role in this diffusion problem? So this is what we wanted to address, and when we compare a cube or this spherical shape or this tetrahedron shape. So you see, this is the phase boundary, the shape of the phase boundary when the hydrogen was diffusing inside of the material, starting from, in this cubic case, starting from a cubic shape until a spherical shape when the hydrogen was diffusing inside of the material. So in this case also you see that the shape remains spherical for spherical particles, nanoparticles. So what is behind the deformations that we observe? Well, what we have are what kind of defects? What we have there are dislocations. So you see here in this case that we don't see, there is you cannot observe any dislocations in there. The atoms remain green, all of them, whereas here you observe some lines of a gray color, meaning that there something going on, some misfit in between the atoms. So meaning that the lattice is not the perfect lattice here again. So in terms of if you plot in detail what is happening there, what you observe are dislocations. So the green lines are dislocations, and the red dots represent the atoms that are involved in that dislocations. You observe planes, particular planes. Not all the planes within the material are active. The dislocations live in a given plane, so that is in agreement with what we have observed in the literature. And you see here, you can see here more details on how the dislocations are evolving inside of the material. They accompany the phase boundary, how it moves inside of the material, and how these the dislocations also get released when the hydrogen moves inside. So this is another image in which you can see what the dislocation is. You see that this is the interface in between both phases, with hydrogen and without hydrogen, and this is where a dislocation lives, is in the interface in between different sizes of the lattice. Here is another movie in which you can see how the hydrogen gets inside of the material, and the dislocations that are created and are released, and they accompany the movement of the phase boundary. Rina, I don't know how much time I have. Keep having in mind that I have.
Well,
yeah,
2 or 3 minutes if you can. I mean,
okay,
that was
okay. I try. Thank you. So here in these figures, you can see again a comparison of the different shapes of the particles, the spherical, octahedral, and cubic one. So you see here the number of dislocations. You see in the cubic one, as I showed before, there were no dislocations and how they evolve. You see that there is a peak in the value of defects in terms of dislocation, and then they release, meaning that the particles, the nanoparticles, are flexible enough so to host the deformation and then release them, which is what is good in order to charge and discharge and uncharge, uh, hydrogen, in this case, inside of a material. So more comparisons of the fraction of phase boundary compare through the simulation, and compare in terms of the total volume of the nanoparticle. There are peaks here, and then they release. Okay, so just to finish, I have shown a lot of atomistic results, and you see I'm not comfortable with this working at this level. Is this level, the atomistic results, are they completely separated from the continuum results? And this is what I would like to show you, that is not the case. So if you consider, I mean, let's focus on the spherical nanoparticle and consider that you have a kind of an inclusion and a matrix. And so you have a solution of this problem, and you can just write the equations and get the results. And this is what the results that you get for the maximum shear stresses that you observe in this layer. So if we compare that with the dislocations, I mean, dislocations means plastic regime. It means deformation inside of the material. So if you compare the results of, I mean, the plot of the maximum shear stresses, and you compare them with the position of the dislocations, what kind of figure they describe when they move together with the phase boundary, you see that there is an agreement in between what you observe here and the shape of the dislocations moving inside of the material. So this is just an example that I wanted to show you, a connection in between atomistic results and continuum results. Also, in connection with the last, I mean, comparison, these are the planes in which you have the misfit dislocations you see here, and they are in agreement with the main planes in which you have the maximum stresses, shear stresses. So yeah, this is another comparison in between the molecular dynamics results and the diffusive molecular dynamics results for this system. I'm going to finish and telling you that we think that this is a useful technique in order to study these kind of problems in which you need atomistic information. You need to take that into account if you would like to describe better diffusion, the diffusion in this case of material inside of another one. And you can really do that taking into account the temperature, which is always there, and avoiding the thermal vibrations. Many thanks for your attention.
Thank you, Pilar. Very, very nice, even though I have to